I welcome you once again to my channel. I am Dr. K. In this video, we'll be having a treatise of the testing of hypothesis. So we talk about the one-tailed test, and some other important things you need to know in the testing of hypothesis. So first, you can see before you hypothesis testing for population parameters with large samples. So when you're talking of population parameters with large sample, you are talking of the sample, that's n, that is greater than or equal to 30. Greater than or equal to 30. Now, hypothesis testing, which involves large sample, is based on the assumption that population from which the sample is drawn has a normal distribution. So take note of that. So it's based on that assumption that population from which the sample is drawn has a normal distribution. And another thing I want you to notice is that when you are dealing with large sample, that is n greater than 30 degree, what you should note is that you use said test. Are you getting it? You use said test. But when you are dealing with the one with the sample is less than 30, are you getting it? So you use what we call the t test. So that's what you use this t test. So let's proceed as we move forward. So now let's talk about the one tail set test for mean, sigma unknown. It's okay, sorry, sigma also known. So sigma is known, and that's the standard deviation. So let's go now. When you're talking of one tail test, so what you're actually talking of, you are talking of a test which is in one direction only. I get what I'm saying? It is in one direction only. That is either it is towards the right or towards the left. I get what I'm saying? Now let's talk about the assumption behind the one tail test. One of the assumption is that population is normally distributed. Are you getting? That's one of the assumptions behind one tail test. So as I mentioned earlier, I talked about that when the sample is more than 30 degree, is more than 30 or equal to 30, they assume that the population is normally distributed. So the same assumption goes for the one tail set test. So now another thing is, if not normal, use large samples. So they said if not normal, you use large sample. So that's that. So and another assumption is that null hypothesis has less than equal to or greater than equal to sign only. So I hope you are taking note. The null hypothesis in a one tail test has less than equal to or greater than equal to sign only. So now let's talk about the for the said test statistic. Are you getting it? So you want to calculate your said test statistic. So that's your set calculated. So you have the formula bar x minus mu x over sigma bar x. So finally you can have it as, so in the simpler form, that will be bar x minus mu all over sigma over root n. So the root n here is your the n here is your sample. Okay, let me start by saying the bar x is the sample mean. Are you getting it? So when you are dealing with testing of hypothesis, anywhere you start seeing average or mean, are you getting it? So that's actually your bar x sample mean. So now your mu is your population. Your mu is your population, the population you are dealing with, as we shall see later. Why the sigma is your standard deviation, and your n is the number of population. Your n is the number of population. So that's that. And another important fact I want you to note at this point is that this formula is used for calculating for finding said calculated. So calculating said, are you getting it? So you call it said calculated. So now one thing I want you to note is at this point is that when your said calculated is greater than your said tabulated, that means you have to reject the alternative hypothesis. Are you getting it? So, but when your said calculated is less than your said tabulated, that means you have to accept that hypothesis. So we move forward. Let's go. So okay, there's an example before me here. A company claims that a can of watermelon seed contain more than 368 grams of seed. So a random sample of 25 boxes showed the um showed the mean 372.5 gram with standard deviation of 15. Yes. They now said test at the alpha equals to 0.05 level. Yes, test at the alpha equals to 0.05 level. So the first thing you have to do at this point, you have to note your you have to state your hypothesis, the null and the alternative hypothesis. So don't forget that we said earlier that the assumption behind the wanted test is that is either the null hypothesis is either is less than uh, as less than or less than equal to sign or greater than or equal to sign. Now look at the statement. So we are so is used as less than equal to a year. That's mu less than equal to 368. Are you getting it? So the company claims that is the kind of watermelon is more than that. So now the null hypothesis is less than equal to 368. So now the alternative is mu greater than 368. So we go like that. We go like that. So continue. Um, okay, okay, okay. Probably there is a mix up somewhere. Okay, let's go. So let's start picking our parameters. So the 368 here is your is the sample. The 368 there is the sample. Are you getting it? So that would be your that okay, sorry, is the that will be your mu. That will be your mu. Okay, let's go. That will be your mu. So now the the 25 boxes we have here, that's our n. The 25 boxes is our n. Okay, 25 boxes our n. Then after that we have our, you can see they said it showed the mean of 3.372.5. Now the mean in this case is what we call our bar x. I said anyway you say average or mean, you are talking of bar x. So I hope you are taking note. Then our standard deviation is 15. So that's that. I think we are good to go. I think we are good to go like that. Um okay, okay, okay. I want to quickly address some things here, like samples. Okay, greater than equals to 30. Okay, all right. So let's go. So now to do something like this, what are the things you need to do? You are looking for your said calculated. Now one thing I want you to notice that there's what we call the said tabulated also. Now how do you get your said tabulated? One thing, you can get your set tabulated from the alpha given. Don't forget that the alpha is 0.05. Are you getting it? Alpha is 0.05. Alpha is 0.05. So alpha is just like saying 5 over 100. Are you getting it? When you take 5 over 100, you get 0.05. Are you getting what I'm saying? So that's 5%. When you subtract 5% from 100%, what you have is 95%. So alpha of 0.05 will give you a confidence level of 95%. Hope you are getting what I'm saying. We give you a confidence level of 95%. Now, I would like to go back and show you something here. Let me go back and show you something here that that your this thing we are dealing with now. This is what we call this is a right-tailed test. A right-tailed test. Now, look at the null hypothesis. Look at the direction in which it is pointing. The null hypothesis. Uh, H1. That's the H1. That's sorry. I mean the alternative hypothesis. That's the H1. Such that mu greater than 368. Are you getting it? Right-tailed test. So imagine you salute a policeman with your right hand. Are you getting it? Now look at the direction of your direction where your elbow will be facing. The pointing part of your hand will be facing. So that's the direction this null hypothesis is facing. Are you getting it? So that's why it is called a right-tailed test. Now back to what I am saying. I said earlier that you determine your what am I saying? Your critical value. You determine it from your alpha. Are you getting it? And the alpha we are given is 0.05. So now 0.05 is the same thing with 5%. Are you getting this? 5 over 100 we give you 0.05. So now 5% minus 100%, you have 95%. Now so 95% now we serve as your confidence level. I hope you are following me. Now for a confidence level of 95%, you have the critical angle. When you check I will give you the constant. The critical value you have is, okay, let me, for a left-tailed test, the critical value for a confidence level of 95% is minus 1.65. Now for a two-tailed test, the critical value for a confidence level of 95% is plus minus 1.96. Now for a right-tailed test, like the one we have here, the critical value is plus 1.65. Hope you are following. So based on that, that's how we got our 1.65. Now this critical value you got will serve as what we call um your said tabulated. Are you getting it? Your said tabulated. So now back to the last one. So now back to the solution. Now how is the solution gotten? After inputting their values, they got what we call an 1.50. Are you getting it? 1.50. Now so how did they get 1.50? Don't forget I said earlier that your bar x is your bar x is your mean. That's the one given in the question as 372.5. So that's your bar x, 372.5. I said anything that has mean or average is always your bar x, 372.5. Then your mu. The mu here is your population, and the mu is taken to be 368. 368. So now all over your standard deviation. The standard deviation here is 15. Then over square root of your n here, square root of n. Your n here is 25. Are you getting it? Your n here is 25. So that's the number of the population. Your n here is 25. So when you input all this, you will discover that you get 1.50. Are you getting it? 1.50. So I said something earlier that your said tabulated is 1.65. I think you remember we got it. So now you will now compare your said calculated to your said tabulated. Your said calculated is 1.50, as you can see. Are you getting it? So you will discover that 1.50 is less than 1.65, which is your said tabulated. Now, and I said earlier that if said calculated is greater than said tabulated, you will reject the hypothesis. Are you getting it? So, but when said calculated is less than the said tabulated, you will accept the null hypothesis. Are you getting it? Now, in our case here, now you will discover that 1.50, which is our said calculated, is less than 1.645, which is our said tabulated. Are you getting it? So as a result of that, we can't reject the no the hypothesis. Are you getting it? We can't reject the null hypothesis. So that means we have to accept it. So that will be all on this video. Thanks for watching. Don't forget to subscribe and share with others. See you later.